a Big Bang still remain constant and the number is still the same?
No, actually, the main mainly neutrinos are formed in stars during nuclear fusion. So, like for example, most of the neutrinos that pass through Earth, like there are around 100 billion neutrinos that pass through every square inch of your body, and all of those neutrinos are actually solar neutrinos. So they're actually created in the sun. So your neutrinos are created in like nuclear fusions through beta decay and like anti-beta decay. Beta minus and beta plus decay is basically two forms of nuclear fusion. So they're actually produced there. So it's not constant. Like the number of neutrinos is not constant; it goes up.
Okay, thank you.
Anyone else? If you have any questions, you can go ahead and ask now.
Sorry, I had another question. So, what's the probability that a neutrino would undergo beta decay to turn proton into a neutron? So, what kind of a possibility is there?
I don't exactly know the answer to this, but your question is pretty interesting because actually it is very related to probability, because in quantum physics everything is probabilistic, and that's also one of the reasons why nuclear fusion is so hard to create on Earth, because one way to get nuclear fusion is by number or temperature. Now the sun's core is, funnily enough, is not hot enough for nuclear fusion, the kind of nuclear fusion that the sun does, but because the sun has so many particles, it due to just because of probability and quantum tunneling, it happens. So probabilistically, I don't exactly know, but yeah, it's it's a pretty interesting question.
So do we begin now, Vinita ma'am?
I think you can start.
Yeah.
Also, because those students are still joining,
Yeah.
but conversation and can. I think you should start. It's already
Yeah.
6:08.
Yes,
Okay.
ma'am. Yeah.
Okay. So welcome back to session number 4 of Fundamental of Particle Physics workshop. I'll give us brief recap of what we did last time, but before that I'll again introduce our peer tutors. That's me. I'm Panthu Chakraborty from a second year physics major from Shiv University. With me I have Devangi Agarwal, who is also a second year physics major, and we have Uday, who is a graduate from SNS SSNS Gurgaon, Noidas. Okay, sorry. Yeah,
It's Noida.
Yeah, sorry. So SNS Noida. So special thanks to Vinita ma'am and Rachna Arora ma'am for making this possible, and we would also like to thank Dr. Arindam Chatterjee and Kenji Nishiwaki for conducting the original session, the original webinar. So I'll do a brief recap of what we learned last session. In last session, we covered the 4 fundamental forces and the properties of those. For example, like the electromagnetic was propagated by photons, then strong was by gluons, then weak from W and Z bosons, and gravity, well, hypothetical particles called gluons. We discussed that and how those forces interact. So any questions you guys have regarding that? Hello, any questions regarding that? Okay, cool. So if nobody has any questions regarding the last session, I would give the control to Devangi to take the session forward.
Yeah, thank you. So we'll be starting with particle accelerators today. I'll just share my screen. Is it visible?
Yeah, it's visible.
Okay. So before going on to particle accelerators, let's talk a little bit about CERN. So how many of you know what CERN is? Would anyone like to elaborate maybe? Anyone? Okay. So I'll tell you. So the CERN, it is an organization for nuclear research, European Organization for Nuclear Research. The actual full form of CERN is actually a French word, but in English it translates to European Organization for Nuclear Research. And a lot of particle research goes on out here, and a lot more than particle also. Then it is also you must have heard of the Large Hadron Collider, the world's largest particle accelerator. So that particle accelerator is sited in CERN itself. And sorry, so there are, and even Indian scientists have a huge contribution at CERN. There are around 400 Indian scientists at CERN which are involved in various subjects, including the LHC, which is the Large Hadron Collider. So here are some pictures from CERN. So Vinita ma'am has shared some pictures from her trip during CERN. So as you can see, this can you see what I'm pointing at? This globe kind of a thing. It's called as the CERN globe, and here basically a tourist can visit, and here they get to know what kind of research goes on in CERN. And this ribbon, the steel ribbon that you can see, it has many discoveries engraved in it. Almost a lot of around 300 or 400 discoveries in different languages. Then these are just pictures from different experiments inside CERN. And as you can see, this is a picture of Nadar, which was gifted by India to CERN when India started its association with CERN in the 1960s. So these are some of the pictures from CERN. So moving on, now before talking about the Large Hadron Collider, I'll tell you what an accelerator is. So a particle accelerator, it drives charged particles. Those particles can either be electrons or protons, since those are the two charged particles, and neutrons are not charged particles, so we don't use neutrons for particle accelerators. So they drive them at a very high speed with the use of an electric field, because electric field can be used to accelerate the charged particles, and they almost made to travel close to speed of light, almost at 99.99% speed of light, which is very, very high. So obviously a lot of energy is also produced during the collisions. So these particles either they're smashed onto a target, or they'll be smashed against each other. Like usually two beams of particles are accelerated and smashed against each other, or onto any specific target. So whenever the collisions are made, usually new particles are formed, or some kind of energy is given out, which the physicists study in order to understand nuclear physics better. So, any questions before moving on? Okay, so if there are no questions, I'll move on. So here, there's a video of particle accelerator at CERN. It shows the complete accelerator complex present at CERN. So before talking about the LHC, let's just watch this video. That was a video of a different particle accelerator at CERN. So as you saw, like particle beams are accelerated in circular rings before they are made to collide against each other. So is there any question regarding the video?
If no one has question, can I ask some question to participants? A very general questions. Um, Tell me, why do we require to accelerate particle? Can't two particle coming closer with a less speed collide and we can get? So, what is the requirement of accelerating particle? Why do we increase the speed of the particle? A very general question. Anyone can answer. The audience, or the student audience. Why do we require to accelerate particle? This is a very basic question because you see the whole of CERN. Can you go back to that slide, Devangi, where you are seeing the cross section of um, particle accelerator, the round cross section of. It was a slide. No, not this one. Yeah, it was in YouTube only, I think. So somebody has raised hand. Can you please answer?
Yeah.
Uh,
Go ahead.
I'm not sure, but is it to increase the force with which they collide?
Can I ask a simple question, Samya? You say force. How force and acceleration are related? A very general question.
So, force equals mass into acceleration.
Okay.
So, if acceleration increases, then so does the force.
Excellent. So you cannot do anything with mass, but you can accelerate to get so that the particle move with a greater force. Right, Samya?
Yes, ma'am.
So now, no, now not Samya. Anyone can answer this because Samya has already given a beautiful answer, and we all are, impressed with it. That okay, force. Why do we require this particle to move with a force towards each other? A general question. So Devangi, you can start from here. Why do we require this particle to move with a greater force? Force. What we are going to achieve in to this accelerated motion of the particle. Over to you, Devangi.
Excuse me.
Yes, darling.
Yeah.
I have actually missed the beginning part about because due to internet problems. Is it okay if you repeat what you did?
Why not?
Yeah,
Devangi,
sure.
can you please repeat in short what you have done?
Right. So
In
I
short,
just
yeah.
talked about what an accelerator is. So an accelerator basically it drives charged particles at very high speed, almost to the speed of light. And these particles then they're smashed either on a target or against each other. And due to these collisions, new particles can be born and or some kind of energy that is given out. And physicists can study these particles into greater depth. So basically, I just explained what an accelerator is. Is that okay?
Yes.
Okay. So then, yeah, so moving on, then I just showed a video of particle accelerators at CERN. And
Devangi, can you please copy this in, and also you can share in message box after your session, or it will be on YouTube also, so children can.
yeah, I'll share the YouTube link.
Not
I'll share it. I also have the access to the presentation, right? I'll share it. You don't have to worry about like.
okay. Please go
Okay.
ahead.
Okay. So moving on, let's talk about the Large Hadron Collider, which is the world's largest and the most powerful particle accelerator.
Excuse me, Devangi. Urjit raised a hand.
Yes, I just wanted to answer ma'am's question. It was because particles, as in subatomic particles, have approximately negligible mass. So that's why the force which they collide with is also around negligible. If they have a greater velocity, then sorry, acceleration, then they would have a greater force to collide with.
Right. Anyone else wants to add anything to that, maybe? Okay. So let's talk about the Large Hadron Collider. So you see this ring that is here. It is a 27-kilometer ring, and this is the Large Hadron Collider. So as we discussed in the last class, a hadron is a particle made up of two or more quarks. So here, like in this, like two energy particle beams, they are made to travel at very high speed before they collide into each other. So like one, they travel in opposite directions. If one beam travels like this, then the other beam will travel like this, and they will meet somewhere where they will collide into each other. And this ring, this LHC ring, it's made up of superconducting magnets. Now, we need magnets because these magnets help in the bending of the particle beams, and also they keep the beam stable. And an electric field is also needed because particles have to have some kind of accelerating force, right? So these electric fields help in accelerating the charged particles.
May I ask a question, Devangi?
Yes, ma'am.
So, and again, this question is to students first, and then you can explain the answer. Devangi, the particle which are going to collide from each other, they could have moved from opposite direction in a straight line and would have allowed to collide. So this question I'm asking because the children are of different age group. So it may be taken to their mind that why do we require a circular path so to accelerate the particle movement? Why not straight? Suppose two students are coming from different side in a straight line and collide. Why they have to move in a circular path so that the speed to accelerate is somebody not Urjit there before Urjit Alia Nagpal is raising hand. Yes, Alia.
Ma'am, I think Alia has left the meeting. She was having some internet issues.
Okay, so she was raising hand. There is a Samya Vash also and Urjit also. So Samya, first you.
I think it is because if they travel in a straight path, then uh, like in a straight path, they cannot make it so long and make it accelerate at the same time before they can collide. Like, and if it was like a square or something, then it would be difficult for the particles to change direction.
Okay, Urjit.
Yes, ma'am, I had a similar point. That was to actually, if the collider is made to be very long, it would require a lot of space. Plus, if it is a circle, we could revolve it a lot of times to get it to that speed that is needed for a collision.
Okay. So, Devangi, can I add some, more points what they said with your permission?
Yes, ma'am.
So it's something like that. When you go to the higher class, you will learn that how the speed of this moving particle, which is moving in a circle, speed directly or velocity directly is proportional to the radius of the circular path. The bigger the radius of the circular path, the more is the velocity. So there is a set formula which has been derived uh, with a simple, electromagnetic effect, or you can say magnetic effect of on moving charge, which you will anyway learn in higher class. But just to give an insight that if they are moving straight line, then that much of speed you can't give. So if it is moving in a circular path, the moment you increase the radius of the circular path, you will get higher speed. If the radius is small, see there are two circles. Can you see, darling? The smaller circle, the first particle move in this smaller circle, what you are saying. So here the speed is less.
This one.
Actually, you can't put so high speed. You cannot. The speed will only increase with the radius. And once it moves in this circular path, the smaller one, then it is projected and it is allowed to enter in the bigger radius path. So that is why the circular path is required. Am I right, Debangi?
Yes, ma'am.
Thank you. Over to you.
Thank you. So also, as you can see, this bigger ring, the biggest ring that is here, it is a future project for CERN where they plan to make 100-kilometer ring for a particle accelerator. So I think they're still like considering this. So it's just a future project. So now the Large Hadron Collider, it has 4 experiments that are there inside the entire system. So the first one is a compact muon solenoid. So as like from the name we can see, it's mainly used to detect muon particles, and it is built around a huge solenoid magnet. So a solenoid magnet is basically, it's like a huge coil which is wrapped around many times, and it has a very, very high magnetic field. So the main purpose of this detector is it helps us to study the standard model. Like we have already discussed what the standard model is in the last few classes. So it helps us in study of standard model. It can also help us in search for extra dimensions, or it could help us to understand what kind of particles make up dark matter. It is like a general purpose detector, so almost like a lot of collisions happen here, and we are almost able to study most of the things from this kind of a detector. So any doubts about this? Oh, okay. Then moving on, we have the second detector, which is the ACCELERATORS detector. It also is very similar to the CMS, and it has the same scientific goal. But then, if it has the same scientific goal, the only difference is that it uses a different magnetic design than CMS. So there's something known as a hadron calorimeter, and hadron calorimeter is a device that is used to detect the particles like quarks and gluons and the other particles. So when we're talking about CMS, that hadron calorimeter is situated inside the magnetic field, inside the coil. So it has to be very compact. But in Atlas, this calorimeter, it is situated outside the coil. So that's why it does not have to be compact, and it can be a longer detector. So here the particle beams from the LHC, they collide at the center of Atlas detector, and through this new particles are formed and they just fly out in every direction. They do not last very long because these particles decay very quickly. So there are detectors all around LHC. As soon as new particles are formed, the detectors are able to detect them, and through which we can study further about it. Any question? Is this okay?
I did not understand. I did not how the particles do not last long, and what makes them like what what is the cause for that?
So, if we talk about quarks, for example, so quarks, they cannot survive on their own. These particles cannot exist independently. So, as soon as they form, within nanoseconds, they just disappear because they're not particles which can survive independently. They need more quarks to survive with each other. Like, as we know, that quark makes up protons. So if we have only one quark, it cannot survive. It will vanish quickly.
Uh, can I add one line, Devangi, here?
Yes, ma'am.
You are also, you can understand this by this, that if something is so small, it's moving with such high speed as it comes out, obviously, you heard of conservation of energy?
No, ma'am.
Conservation of energy, that energy cannot be created, cannot be destroyed. It only converts from one form to another form.
No, ma'am. I've not heard of it.
Okay, so this is the truth. that the energy, one, like suppose you have something in your hand, let's say a plate, okay, so it is in your hand and you are holding it. So the plate has got some potential energy, right? Because it is at some height. The moment you leave it, it starts moving down. So the potential energy gets converted to kinetic energy. Are you getting it?
Yes, ma'am.
And as it hits the ground, it doesn't mean that it got stopped means all the kinetic energy vanished. No, it got converted into sound energy because you will hear a sound, right?
Yes, ma'am.
And you will also, the moment it collides, there will be friction, and so obviously some heat also. So this is the law of universe, conservation of energy. Energy cannot be created, cannot be destroyed. It only transforms. Exactly same way, there is a mass conservation also. Total mass is fixed, right? So mass cannot be created, cannot be destroyed, right? But then uh, there was a theory, there was a law which which unified these two, and this is called energy mass conservation law. So if something is moving with a very high some quark or some, like when ma'am says, Devangi ma'am is saying that it vanished, it means that mass has got converted into energy. A simple example: when you display rocket, in Diwali, so that the material which is burning is mass, right?
Yes, ma'am.
And as it goes up, you see the fires and heat and smokes, and it doesn't mean that the mass is vanished. It got converted into light and heat energy, right?
Yes, ma'am.
So then ma'am is saying, Devangi ma'am, that the quark, they cannot live in for longer time. They disappear. They got converted themselves into energy. Am I right, Devangi?
Yes, ma'am.
Thank you. So, a good question, and I hope you all enjoy and you all understood.
Yes, ma'am. Thank you.
Thank you. Over to you, Devangi.
Thank you, ma'am. Okay, so moving on, we have the next experiment, which is called the LHC Beauty, the Large Hadron Collider Beauty. So here it is a very interesting one, as this experiment helps us to investigate differences between matter and antimatter by studying the bottom quark. So since like bottom quark might be, we might get a bottom quark by any collisions, but since these quarks do not last very long, so there are detectors all around the LHC beam. So these movable detectors, they catch these bottom quarks, or also known as the beauty quarks, and these quarks helps us to understand the differences between matter and antimatter. So this is more of an interesting experiment at LHC. The next experiment, which is the last one that we have, is
Raising hand.
yeah.
I wanted to ask, how does the bottom quark help us in the discovery of antimatter?
Not discovery of antimatter, but it helps us to study the differences between matter and antimatter. I do not exactly know how it does, because I did try reading upon it, but it was something very complicated and I didn't understand it completely. That's why I didn't bring it up here right now. But maybe I can look up a little more on it and get back to you.
Also, Devangi, you give whatever point like the kids are asking, and if anyway you get stuck somewhere, you give this as an assignment. Let's everyone research, right? Let's
Yes, ma'am.
everyone research. Vidush, are you getting it?
Yes, ma'am.
And we will also take help of Dr. Arindam to address this question. So please note this question.
Yes, ma'am. I think this would be like a good question to ask Dr. Kenji and Dr. Linton.
Yes, excellent. Thank you.
So then the last experiment that we have is ALICE, or Large Ion Collider Experiment. So here basically it is mainly studied, like this experiment is basically dedicated to heavy ion physics, like very heavy particles are studied here. Particles which have like high densities and high energies. So they are collided in this experiment and their nature is studied. So these were the 4 experiments at LHC. So any questions about it? Okay, so there's this one last video that I would like to show you. So here's like a hypothetical situation, like what happens if a black hole opens at CERN. Since we all know a lot of energy is being created at LHC, very high, like particles are at very, very high energy. So since the energy is so high, there is a possibility, a hypothetical possibility that a black hole might open.
Okay,
So
Devangi, before we display this video, I have a question to the students. What do you understand by antiparticle? And what is there some proof that antiparticle is there? These two questions, has anybody made, has any of the antiparticles made in any of the labs? This is Madhav Sharma raising hand. So please.
Yeah, so I thought what antiparticle is, and I searched on Google and I found out that they are the opposite of particles. So what I made up was that if there is a proton, then its antiparticle would be neutron. But I wasn't confirmed.
not neutron won't be an antiparticle for a proton.
Sorry,
Positron
electron.
maybe.
It'll be
Elect.
electron. Neutrons have a
Positive.
neutral
Yeah.
charge.
So
Yeah.
so I have a doubt. So is it right?
Electron is not an antiparticle of proton, because if electrons and protons were antiparticles, they would not survive, because matter and antimatter just cancels each other. But
Resulting in a big blast. Basically, a lot of energy is released.
yeah, right. So, but antimatter, since like very little of antimatter is present in this universe, but there is, I think, an antimatter factory at CERN.
Yes.
Uh,
Yes.
so
Right.
there a lot of research about antimatter goes on.
Uh, Interesting discussion
Can I
going
say?
on. Yeah, Samya, please go ahead.
I believe that there is supposed to be as much antimatter as there is matter, but we don't actually know where that antimatter has gone.
Yeah, because like from the Big Bang, matter and antimatter were produced in equal amounts, but then matter survived and antimatter could not. So there's like less amount of antimatter and more amount of matter in this universe.
Uh, Also, there is a this thing research going on, Devangi, and all audience. When I went to CERN, I went to anti matter factory, and you will be surprised, children. I will show you the video also sometime. That yes, CERN is has made anti hydrogen, antimatter also, obviously. Then only anti hydrogen can be made. And as you know, that hydrogen has got its composition like what is there inside proton and neutron, etc. and all. So they made anti-proton, they made anti-electron, and obviously, and they have made anti-hydrogen. And so there is a proof that yes, antiparticles are there. Also, research is going on that there may be some parallel universe. Who knows where the antimatter went? So obviously, whole of the antimatter will not disappear into energy, but they may be somewhere making a parallel universe. So these all things were told by seven scientists when we visited to antimatter factory. Thank you. Somebody was raising hand.
Yeah, Madhav.
Yeah. I had a question. If there is antimatter, then how is matter surviving?
Right. So I said right, antimatter is
Magnetic fields.
yeah, and antimatter is in very low abundance, and we do not know where it is exactly. And like ma'am said, there might be some other source where antimatter is vanishing into.
So why didn't they cancel out each other, as you said, like when Big Bang Theory was done?
I am not too sure about it.
There are a few theories about regarding this. One theory says that one theory states that both were created in equal amounts, but somehow the antimatter can't what Vinita ma'am said. It's in a different parallel universe, an anti-universe, if you may. But
Yeah.
that's a very theoretical concept. And the second part was maybe there were more amount of matter was created than antimatter. So the antimatter cancelled out, but a bit of the matter left.
Was left
Yeah.
behind.
Oh,
So
okay.
there are many theories. Nobody knows the answer to what happened to the antimatter.
Okay.
Right.
Still going on.
Okay,
And
thanks.
Ruben Sharma, you also have a question?
Yeah. Last year in sixth grade, I watched a video, and well, then it's not really important what was in the video, but could the antimatter be used to like create energy? Like
Yeah.
that could be used in like
It
everyday
can.
appliances to power the
Since
TV or
it
something.
is also matter, so when it will decay or when it will disintegrate, energy would be created.
So
Okay.
theoretically speaking, yes, you can use antimatter to create energy. In fact, that is the most efficient way of using energy. For example, right now, most of the energy that we use is either chemical energy, like through chemical process, that is coal, petroleum, through combustion, or physical, that is solar, then wind and all.
Right.
Uh, they are very bad at converting mass into energy. They're horrible. So that's why, like, so when if we can use antimatter, then we can actually get 100% efficiency of energy. So, like, basically, you take one molecule of antimatter and one molecule of matter, you collide them, and you get two X-ray photons. So that's a lot for just one particle. So theoretically speaking, yes, if we had a huge mine of antimatter, we could we will never have to worry about the whole energy crisis ever again. But again, unfortunately, you don't have enough antimatter in the universe existing normally. The only antimatter that we is like created is due to like some nuclear fusion in
Nuclear
stars.
fusion. Right.
And
Yeah,
even if we had a way to like find antimatter, we wouldn't be able to contain it
yeah, we can
because
contain it through a lot of
magnetic
magnetic
fields.
fields. Yeah, but again, it takes too much energy and money to create antimatter and then store antimatter. So, like, when we convert it to energy, we don't get any delta money back. So basically, it's a horrible way to do business.
Excuse me.
Yeah.
Yep. Go on.
Is it okay if I ask a question?
Yeah. Go ahead.
So you said that there is antimatter, but in a very small amount. So, um, like, uh, what is that small amount of antimatter used in?
Used in as in what is the purpose of antimatter?
Um, I like it. My question is divided into two parts. Like, what is the purpose of antimatter, and like, where is it used?
So, like purpose, like as Pantho said, it could be used in harvesting energy. But since we do not have enough antimatter or antimatter disintegrated or went to some other place, so we don't know where antimatter is. But it can be used to create energy.
But if you're asking what is it used in currently you antimatter isn't used anywhere.
Yeah,
It's
currently it's not.
Yeah, like the only places where antimatter is created in the universe is nuclear fusion in stars, and a lot of those antimatters also meets other, and that's mostly positrons. So that's antiparticle of the electron. So a lot of time it just meets another electron and disintegrates. So actual antiparticles, there are not a lot antiparticles left. Another way antiparticles are created is through like the pion that I discussed in the last class. Pions are made of one quark and one antiquark. But again, they always cancel each other out after one, like after, like, they exist for a very short time and then they cancel each other out. So you can't extract any antimatter from that.
Okay, thank you.
Any other question before I show the video?
I have one more.
Yeah.
Um, I just wanted to ask that all living things need to produce multiple times or reproduce to like exist. But so if antimatter is you is like I'm not very sure how to express this, but like if how is antimatter created?
Antimatter is created in nuclear fusion, right? Like Panthu said, and but since antimatter cannot, so antimatter and matter they cancel each other. So when antimatter is created, it will find its counterpart in the matter, and it will just destroy each other, and then energy will be released. So we do not have antimatter as of now, like somewhere that where we can store antimatter and make more antimatter, but because antimatter is really it does not survive a lot. It finds it other part in the matter and it just disintegrates.
Okay, thank you.
Okay. Any other question?
Also, Devangi, this is important to convey to students that at the time of Big Bang, equal amount of matter and antimatter were created, right? So this is
Yes,
because of symmetry of universe. So if there is something like day, or I can explain you in a simple way, day there is a night. If there is morning, there is evening. If there is so that time only matter and antimatter equal amount were created. Over to you, Divan.
yes, ma'am. Okay, so shall I show the video now if there are no more questions?
Alia, do you have your hand raised, or do you have a question, or it's just raised?
It's just raised. I forgot to lower it.
Yeah, it's okay. No
Okay,
problem.
no problem. Okay, then I'll show the video.
How did we get here? Let's roll back a few days. This is CERN, the nuclear research laboratory on the border of France and Switzerland. It features the most powerful particle accelerator on Earth, the Large Hadron Collider, or LHC. What does it do? Well, it accelerates and collides particles at 99.99% the speed of light. And maybe it could produce the very first lab-grown black hole. How big would that black hole be? What precautions would you need to take not to get sucked in? And how long would it take to destroy the entire planet? This is What If, and here's what would happen if a black hole opened at CERN. Black holes. Gravitational matter devouring monsters traveling across the universe on their own terms. Some of them are so big they could gobble up the sun in a day. Could scientists create one of those at CERN? Theoretically, yes. But could a lab-made black hole be the end of Earth? Let's see. The LHC is a 27-kilometer ring of superconducting magnets. Inside, it accelerates particles to move at almost the speed of light. These particles are bound to collide, and when they do, they produce enough energy to create new particles. We're talking about very small amounts of energy here. The numbers are so tiny that scientists came up with a new unit of energy to measure particle energies at that scale. It's called the tera-electron volt. 14 tera-electron volts give you new particles. 1 followed by 19 zeros of tera-electron volts would give you a black hole. Already picturing doomsday scenarios? That's very much in the spirit of What If, but that's not how it would go down. If one of the experiments at the LHC ended with scientists creating a black hole, that black hole would be microscopic, as in quantum level small. It would have a mass about 40 million times smaller than the E. coli bacterium. It wouldn't get out of the accelerator and rampage across the planet, chewing up everything in its way. Well, it could get out, but because of its laughably small gravitational pull, it wouldn't attract a single piece of matter. The black hole would lose its energy through what's known as Hawking radiation long before it could gain any substantial mass, as if it never existed in the first place. Even when folks at CERN build a next-generation lab, the future circular collider that will outpower the Large Hadron Collider, will still be pretty safe. For a lab-produced black hole to potentially cause any damage, it would need to have a mass of at least 0.00002 grams. That's about 50 times smaller than the mass of an ant. It would take that black hole 9 octillion years to reach the size of 1 kilogram, and another decillion years to swallow up the Earth. The whole process would take longer than the age of the universe. I'd say no need to worry about it at all. The Earth doesn't get destroyed every time physicists do something cool, unfortunately. But if something does go wrong and you find yourself one-on-one with a black hole, don't panic. Tune in to our new show, How to Survive. There, we've got you covered for any life-threatening scenario to help you survive whatever awaits you.
Okay, so that was the video. Anyone has anything to say about it?
I want to say something. I also have a question.
Okay, go ahead.
Yes. So my question was that you said that the video says that the matter can be sucked in by black holes, but can antimatter be sucked in by black holes as well? If we I'm not sure, but like if uh, it's not possible, but like if we ever see a black hole.
I guess it can be.
Yeah, antiparticles can also be sucked into a black hole, and the reason for that is no matter particle or antiparticle, both have a positive mass. Your mass as a quantity, it cannot be negative. So if there's a if there's a electron and an anti-electron, that is a positron, they weigh the same. So according to gravitational pull, like if we go to if we look at the theory of gravitation, ideally they should follow the same law. So because
Yeah.
black holes only like they only function in the gravitational force, they can easily suck in particles and antiparticles alike. The black hole doesn't discriminate.
Okay, thank you.
Anything else?
So you had said if anyone wanted to speak about the video. So I did not understand by what you meant by speak.
What meant by what?
You by speak you had told us that if we wanted to speak anything about the video,
Like,
but
I meant like any comments or any discussion, anything related to it.
Any questions do you have regarding the
Yeah,
video?
anything.
Yeah.
okay, thank you.
Devangi, can I just take 1 minute to show them antimatter factory right here on screen, if you allow?
Yes, ma'am. I'll stop presenting.
Okay.
Ma'am, you are on mute. We can't hear you.
Sorry. So if you see this, these children are from Vidyagyan and obviously from SNS Noida also. And this person was from somewhere Italy. And yes, we visited. In fact, I have video of making them understand how antiparticle was made in lab. So maybe I'll try to find. I'm not able to get, or I'll show you. So this is antimatter factory. Can you see, children, on this screen? So you see this is a combination of blue and orange, and there is a tunnel type of thing which is going inside all this, and it's a round in structure. Okay, so the blue one is magnet, which is actually giving direction to the antiparticle, and these are the electric field. So always remember, electric field gives the speed to the or accelerate the particle, whereas the blue one gives the direction. As it is round in structure, the magnet has to be installed every turning, otherwise it will go straight. So as it comes here, the magnet turns it. As it comes here, the magnet. This is your antimatter factory, and we were standing right on top of this and understanding how anti-proton was created. And it was, maybe if you are interested, maybe I will try to look get that video also and show you that how these are the supercomputers of the CERN. We went deep inside, and maybe once I find the video, will show you how the scientists of CERN explain that how anti matters were created, and they have only succeeded to make anti-hydrogen. They haven't gone to next level. Just one element, the most primitive one. They haven't made a neutron or it's only protium. I think protium and neutron. These two only they have made. Over to you, Devangi. Thank you. I hope these pictures will excite students. And who knows, Devangi, your students, which you are seeing over here, one of them will work in CERN and they will remember you, Pantho and Uday. Thank you.
Thank you. So anyone has any questions related to anything that we talked about today?
I do have a question.
Yeah.
What if a person gets stuck in a particle collider?
That would be the end of the person, I guess. I don't know.
But
That did happen to one person, interestingly.
yeah, but he survived.
Yeah, he did survive. So the thing is, when you're talking about particle accelerators, we have particles which are, of course, they're very low in mass, but they're moving at very high speeds. But at the same time, they aren't radioactive particles, right? So they can cause mutations. They can still tamper with the atoms in your body a bit, but they aren't they don't have properties similar to the what we usually call radioactive particles that have much more devastating results in humans. So the thing is, yeah, the person who did stick his head inside a particle collider by accident, he of course incurred a lot of damage because there is something moving at almost the speed of light. So that is bound to have some effect from a mechanical perspective. But if you are thinking from the perspective of biology or chemistry, due to the properties of these particles not being similar to the radioactive particles, they don't really have an imminent or a critical effect on your health in that way.
So there's a 50-50 chance.
I don't know if you can boil it down to I think that would be an oversimplification to call it a 50-50 chance. But yeah, you can call
So
it.
either you get a hole burned through your skull or you survive, but you get
No, you will never get your it's the particles don't produce so much energy that they'll burn a hole through your skull. A lot of the problems which you might face if you stick yourself down in a particle accelerator will most of the damage will actually be from the very high magnetic and electric field rather than the particles. So
okay.
yeah. So yeah, basically, if you for example, if you go for an X-ray or a CAT scan or something, you like people ask you to remove any kind of metals from your body. So very similar, and like the magnet used, like the magnetic for the electromagnetic used in these colliders are much more stronger than the magnet of the earth, like the magnetosphere of the earth. So if you have a metal there around your neck or anything, that metal will actually start to like create current because the metal is there. That might shock you, or maybe that metal can like pull you towards that magnet if it's like if it's strong and if it's like strongly tied to you. So there are problems which can happen because of that. But if you are going there without any kind of magnetic thing or anything, you won't probably you won't have a lot of problem. Yeah, you might get some burns or electric shocks, but nothing like, well, obviously I am not saying that a person should go into the particle accelerator because it's still very harmful, but it's not that harmful.
Panthu
Basically, the
also,
particles are not the immediate threat in the particle collider.
Yeah.
also this is important to add here, Pantho, that see in particle accelerator, it is not that one quark is coming from this side and one quark is coming from that side is allowed to, because the chances of collision is very very less. So a beam of particle is sent, right? If there is one particle colliding with one, the amount of energy liberated will be minuscule, and it may not harm you or me, or maybe not that much. But think of a collision taking place where the beam of particles are coming. Because the chances, see, it's a tunnel, and in that tunnel, if particles are coming from opposite side, need not necessary they will meet. You understand like this, they will just surpass because they are so minuscule. Tunnel is so huge. I'll show you the picture sometime of that also. So if one particle is colliding, then amount of energy released is very less. But it doesn't happen in particle accelerator. They allow a beam of millions of particles to move from in opposite directions. So some collision takes place, right? So think of the amount of heat energy liberated that time, and so that is devastating. And for that tunnel is always always in a chamber, you can say, or that tunnel what Devangi showed just now, the cross section is always in a chamber of liquid nitrogen or something which keeps cooling it down. Okay, that this is important. Panthu has shared some video, I think. So over to you, Devangi and Panthu.
Yeah, I just shared the black hole and CERN video for anyone who wants to check these out and like watch it again.
Okay, I guess. Anything else?
Okay, so if you guys don't have any question regarding this, then we can we have a small assignment planned for you guys. It's basically it just has like 6 questions, and it's yeah sorry yeah it just has 6 questions, and we'll give you around 7 minutes to do it. They're very easy questions. I'll
Yeah,
share the
like
Google form.
just MCQs. So you just
Yeah.
need to mark the right answer.
Yeah, it's based on today's and yesterday's class. So I'll
The
share
last
the
3 classes.
yeah
And the class before the last one also.
yeah the questions are very easy. I'll share the link, Google form, and please submit it as soon as you fill it. Thank you.
See the discussion on antiparticle and all this, I'm planning to or thinking of Pantho. Maybe end of the session we may invite Dr. Arindam, or maybe I'll try to loop in someone, and give a closer to the session. It's going on so beautifully with you three. So also, Uday, do we have some feedback form or something? How can we improve, or how was the session, etc., which can also be given in the message box, which students can.
Maybe we can create one and send it to everyone by mail.
Yeah, I think, yeah, we can talk about that.
Yeah, guys, are you doing the Google form? You guys are doing the Google form, right? The quiz.
Yes.
Yeah, cool. I just had to inform one more thing. That is, there will be a small quiz like this in every session. It will just be like the very few questions just regarding this, and by the end of the all of the sessions, by the end of it, the person who got got their answers correct and all, the 10 highest scorers, we'll give them few prizes.